In this video, we'll take a look at the steps we can take to create our own static library. So the program that we will use is AR. It's the archive program. And the AR program creates archives or collections of .o files in a single .a file. That is, all the code, all the functions that would go into a whole bunch of .o files can be put into a single .a file so that you can compile, let's say, a main program plus a .a file instead of compiling a whole bunch of small .o files together. Okay, so let's just go through the steps in doing it both ways. So let's try it both ways. So here we have a bunch of C programs. So main is a very simple one. It uses some of the functions that we've been talking about in this lecture earlier in the earlier videos. So if you look at main.c, what it does is it has a pound include stdio.h. It declares or gives you a function prototype. This is also a function declaration, but not the definition of a function called print length, which takes as parameter a single pointer to a const, a const pointer to a car. And the same thing with copy string, only it returns a pointer to a car. So these are functions that we talked about, and I'll show you the code for this in just a second. So in main, we set up two styles of setting up strings. We say str1. Remember, in this case, we can go in and change individual characters in the string. In str2, you're not supposed to. I believe you can, and you probably will be able to probably will be able to actually change some individual characters, but you shouldn't. This is meant not to be changed. So when you define it this way, remember, if you're saying that str2 is just a pointer, and it's going to point to some chunk of memory which is allocated in sort of a global data section. And that's where this string is stored. This string, on the other hand, as we saw, this is an array that's allocated on the stack, and so all of this will go into some area of stack memory. So then we call this print length function with str1 and str2. We copy str1 to str3. If everything works, it should allocate some memory. So the things to note are that copy string, if you remember, we set this up a while ago. I'll show you the code in just a second, but this should allocate memory on the heap. So you're making a copy of a string that's allocated really on the stack. You're going to copy it to the heap. Here, this is memory that's allocated in some str2 is allocated in some global data area or of memory where some constants are stored, things like that. And then you're going to copy it from there into copy string should make a chunk of memory available on the heap. Sorry. So copy string str3 will be point to some place in the heap. So will str4. str1 will be on the stack. str2 will be will point to a chunk of memory in the global data section of our program. So although they look very similar, they are actually, it's interesting, these are in three different places: heap, stack, and global data. After that, we just print out str3 and str4 to make sure that they actually do work. Okay, so let's take a look. Let's take a look at print length. That's simpler, I believe. Print length.c is very small. It declares a length function which it uses here, and all it does is to call printf, and to do that we have to pound include stdio.h, and it prints out length of string, whatever s is passed in to here, prints that out, and then it says is a decimal or an integer number that's returned by this length function. So let's look at that too. Cat ngth.c. So this is using that technique that we saw not too long ago, where we can say that s It's a pointer, it's a const pointer, and to be able to do that without any warnings, to put in a const here without any warnings, we use this array index notation rather than pointer arithmetic. So that's a trick that we, or not a trick, it's a technique we talked about a few videos ago. So if you don't remember this, definitely take a look back about 2 or 3 videos ago. So this simple loop, all it does is look for, it keeps looking at s sub 0, s sub 1, and so on, up until it finds a location in this array that is a null character. When it becomes null, it exits the loop. Okay, so you can pause the video, take a look at these individual files. There's 4 of them. Main, length.c computes the length, printlength.c computes the length, prints it out. Copy string returns a copy of a string. Oh, let's take a look at that. Almost forgot. Okay, so this uses calloc. To be able to use that, we pound include std lib.h. We use length to find out how much space to allocate for this a copy of the source string s. So you find the length of s, add 1 to it for the null character. These are measured in bytes, so that's why we have this multiplier 1. And we allocate this much memory, and p points to it. We make a copy q, and then we sit in this loop and copy everything from s into what q points to as we bump up s and q until the thing that s points to is a null. So that is until you get to the null character, null termination. Okay, so pretty straightforward. If you want, pause the video and code this up. This is copy string.h, and you can, all the others are also in this video. Okay. So one way to compile all of this would be gcc -c gth.c. Alright, what this does is create a length.o. You do the same thing, gcc -c main.c, and this should create a main.o, gcc -c copy string.c, gcc -c, finally print length.c. It doesn't matter what the order is. You're just creating a .o file. For each .c file, you're creating a .o file, and so on. Okay. And then you can gcc -o, create a main program or executable out of all the .o files. Main.o, length.o, copy string.o, and print length.o, and it worked. So print it out, run the program, and you get everything working, so no problems. Length of the string, this is string number 1 is 17, string number 2 is 17, string number 3 you copied it and it looks fine. It is string number 1. String number 4 is also has the same thing as string 2. So compare the output, that's the output, versus what it's supposed to print, and I think everything looks like it's working. Okay, so notice we had to do a whole bunch of compile steps. Let me remove all the .o files. Actually, I don't need to. So we compiled each .c file into a .o file and then linked them all together. So one way to handle all of this, if you need to do this a whole lot, would be to say AR, use the AR command, and if you want to see the man page, there should be a man page for AR. Create, modify, and extract from archives. So take a look at that. we are going to just use it for one thing, that is to create a single library. Call it anything you want. My functions.a. So archive files end at the .a. For a lot of files, it doesn't matter what file extension you use, but it turns out for libraries, they all have to start with a lib. I didn't mention that, but the way you'll see why in just a minute when you use the GCC to link to this library. But they have to start with a lib. They have to end with a .a. Although you can get around that restriction too. Okay, so let's create a library out of length.o, and it has to be a .o file, and print length.o and copy string.o. And it looks like it worked. It even showed us a table. So it looks like, I believe we don't need to run ranlib. So on this system, on Linux, you don't. If you're using a lot of BSD systems, will require you to run ranlib before you can actually use this library file. So here it is. Here's libmyfunctions.a. So if you take a look at the size, it's 334. It should roughly add up to this 1044 plus 888. That's about 1900 plus this one. I guess it's a little bit bigger than the sum of those 3 .o files. Okay, so now that we have this static library function, what can you do with it? Now you can say gcc -o main. You can say main.c or main.o is fine, maybe since we have it. And you can say -l, that is, we're saying the path to the library is in this current directory. And here is the name of the library. You skip the lib part and you say my functions. Okay, so if you have some libx, that is whatever x is, .a, you say, when you link, you say -l and then x, whatever x is. So in this case, our x is myfunctions. And so to link to that library, you have to say minus lowercase l, that's a minus lowercase l over here, and then whatever comes after the lib and before the dot. Hope that works. Alright, looks like it did. And then we're going to run it. All we have to do, let's just do an ls -l, and it looks like it was recompiled just now, comparing the date, comparing the time. It looks like it was recently compiled. Okay, so now we run main, and there it is, as good as new. Still, everything worked. That is, what we did was we created .o files, 3 of them, for copy string length and print length. Created a lib file or archive file, libmyfunctions.a, out of that using the archive program, AR program. And then once we do that, all you have to do to compile is something like this. GCC -o, you don't have to recompile them or anything. They're all ready to go. Alright, so for a small number of files, it's not that big an advantage to create a .a file, but typically .a files can be maybe hundreds of kilobytes, maybe a megabyte, maybe many megabytes in some cases. So that would be the advantage if you have hundreds of these .o files. You put them all together, and then you can link them all in one simple step.